Hello, my name's Callum McClure. This was a recent presentation I did for the Intergovernmental Buildings and Settlements Roundtable. I thought it would be a useful resource for introducing people to the key concepts of 3D models. I will talk from both a high level and also get into some quite technical aspects of 3D models. This is a short 15-minute presentation, so I apologise if we gloss over some topics quickly. We're here today to talk about the new UN GGIM Buildings and Settlements theme released in 2018 and 19. This theme, along with three others, was adopted by ANZLIC in 2020 as one of the themes of the Foundation Spatial Data Framework, the FSDF. The focus of today will be 3D model concepts related to buildings and settlements. Why do we need a buildings and settlements product? Well, they are linked to the UN Sustainable Development Goals. Build resilient infrastructure, promote sustainable industrialisation, and foster innovation. To make cities and human settlements inclusive, safe, resilient, and sustainable. And to ensure sustainable consumption and production patterns. The definition of a building, as defined by the UN GGIM, refers to any roofed structure permanently constructed or erected on site for the protection of humans, animals, things, or the production of economic goods. And settlements relates to a collection of these buildings. And I assume if you're watching this presentation, then you'll be already aware of the many use cases of building models in smart cities and digital twins. These are asset management, risk and emergency management, spatial analytics, statistics and reporting, performed by our federal, state and local government and agencies or utilities, as well as by the private sector. And of course, the urban development and planning, the future planning, including not just the built form, but how our public interacts and experiences urban spaces. In the COVID lockdown world, things like the important strategies of 20-minute cities. We'll now cover some high-level 3D model terminology and concepts. Firstly, we have LiDAR, digital elevation models, and digital terrain models. This is the survey accuracy that's tied to our survey control network and builds a foundational accuracy for which our digital twins and 3D models are built on. Then we have LOD 0 and LOD 1 models, terminology I'll describe later. These are building footprints for both the macro analysis but also micro decision making on individual buildings, such as intersection of a building with a flood polygon by a water authority. And then we have the LOD 2 and above building object models, which are used for urban planning. These data sets underpin digital twins. And then we have medium and high resolution photomeshes, which are great for modeling both the natural and the built environment. With the higher level resolutions, ideal for creating a spatial digital twin of an individual asset, but also just for general visualizations or immersive VR experiences. So, the terminology. A 3D model is used to both describe a photomesh on the left and object models on the right. On the left, common names include a photomesh, photogrammetric mesh, 3D integrated mesh, 3D textured mesh, a reality mesh, a triangulated mesh, or what I like to call it, 3D imagery. And I'll describe this dataset in more detail later. On the right, we have object models, building models, city models, level of detail models, LOD models, 3D information models, context models, and obviously buildings and settlements. Today, I'll be referring to the terminology of photomesh on the left, and on the right, I'll be referring to building object models, LOD models, or level of detail models. Photomeshes. If aerial photography is a flat piece of plastic, then a photomesh is a fully formed coffee cup lid in 3D, like a piece of cling wrap draped over an entire environment at a single point in time. This includes the buildings, the terrain, the vegetation, stationary cars, and any above ground feature. A photomesh is a single epoch, a single object, which is a snapshot in time. I do like to refer to it as 3D photography. Think of it as cross between a LiDAR point cloud and aerial imagery. You can see the image on the right of the photomesh. It is made up of many thousands and millions of triangles all stitched together with photography applied. Now on to building object models, LOD models or level of detail models. LOD models are just one component of a city model. There are other classes, including things such as bridges, tunnels, or street furniture, and all these different classes follow a similar level of detailed description as on the right. The first row are the LOD0 models. These are the 2D building footprints or outlines. The next row is the LOD1 models, the same footprint with a height extruded to maybe the building eave or maybe the min or maximum elevation of the building. And then we get down to the next row of LOD2, which includes the definition of the significant roof form, noting only LOD 2.3 includes the modelling of the building eaves or awnings. The next row is LOD3, with the later stages of LOD3 including the facades of the geometry of the facades. Now with any of the models above LOD 2.0, they can be untextured, grey or white, or they can have a textured apply using real-world photography, or they can even be textured or symbolized using false textures from a library of bricks or windows or roof material types. So, to try to remove some confusion, or maybe even creating some more confusion, LOD models on the left is what we use in the GIS world. These are used to define the external geometry of a building. And it's how we model large extents of the built environment for whole entire cities. On the right, we have building information models, commonly known as BIMs. These come from the engineering space and refer to more of the internals of a building, used for construction or design. These BIMs include information on the thickness of walls and the build materials, can be used by quantitative surveyors and in asset management. If you're getting confused, just remember that on the left, the GIS LOD models use the numbers 0, 1, 2, and 3, and on the right, the engineering BIMs use LOD 100, 200, 300, and 400. And here are some more examples of those LOD1 models. The top left is an example of LOD0, two-dimensional building footprint or outlines. And the bottom right is the same data set, but with heights applied, extruded, LOD1. A quick technical note. This is from the New Zealand Building Data Dictionary, a great resource I'll link in the description of this video. There is a difference between a building footprint, the footprint of the building on the ground in its true location, and the building roof print, the outline of the roof in aerial imagery, including any building lean. This topic deserves its own presentation. It's important for us to have high quality imagery and LiDAR standards to reduce the building lean in our ortho imagery, to ensure that the features that are extracted are as close to the building footprint or its true location on the ground. And here is an LOD2 plus or LOD 2.0 and above building object model of a high value urban environment. On the left and right is the same data set. On the right, we see how textures can be applied and how they can give more detail and context to a building facade or its roof. I'll note that if you have textures of facades showing, I'll note that if you have textures of the facades, geometric features like windows are shown, This negates the need to actually model the geometry of the windows in your 3D model, like we see in LOD 3.2 or 3.3. You'll note that the textured models on the right look a little bit like a photo. On the left, you'll see that the untextured models can actually display visually to the observer more of the geometric information without textures displayed. These models in this scene I call LOD 2 plus, LOD 2.0 and above. This is because simple residential buildings here could be defined quite simply with LOD 2.0. They're fairly simple. But some of the more complex buildings, such as a church or a heritage building, might be modeled to LOD 2.3 or LOD 3.0. So, comparing the two and the differences. I believe building object models, LOD models, are the response to the buildings and settlements theme. These objects are data-rich, attribute-rich, suitable for analysis and interrogation, but a photomesh is still has a critical role to play, like our ortho imagery, or maybe building classified LiDAR point clouds. Each state jurisdiction, with their own situational and environmental needs, will likely apply a different solution to buildings and settlements, with different combinations of aerial imagery, LiDAR, and photomeshes. I'll now talk about the methods of extracting these building models. Feature extraction using a manual mapping technique is the direct observation of individual features, each and every single building vertex or polygon, modeling the building to a desired level of detail, noting that there will be some generalizations. This manual mapping could be LOD 0 models, building footprints, extracted from ortho imagery, or in the case shown, LOD 2 models from stereo imagery, modeling features from nadir, top-down, and oblique imagery. But this could have well been modeled from a LiDAR point cloud, for instance, or even from a street survey. The result of this manual mapping is a high-quality, high-confidence model, suitable for the maximum number of use cases. But obviously, this manual mapping is time-consuming and high cost in both production, procurement, and also QA. Similar type of LOD2 models can be created automatically using a procedural or parametric algorithm to generalize the roof form into general types like flat, gable, hip, or sloped. These are great ways to create a general approximation of a whole entire cityscape with a large-scale automation. However, in this case, outputs might not be suitable for some of the high-end, high-value use cases, like say submitting evidence to a building planning tribunal hearing. Also to note, these solutions usually utilize high-cost LiDAR inputs. However, they can utilize some imagery-derived elevation products. And thirdly, we have artificial intelligence, machine learning or deep learning, which is just a tool that we use for feature extraction with great opportunity. It is scalable, it's repeatable, it's uniform, and replicates usually a fairly simple human analyst task, such as extracting a building footprint from ortho imagery. But it's not without errors. Also, a human analyst is required to create the training dataset in an iterative process, mitigating error propagation. But also, the final machine learning results that come out will still have errors that require human intervention and human QA. And maybe these errors can't be efficiently removed by improving the training dataset. So, the results of this machine learning extraction still require human intervention in post-production QA to uplift the final delivered product to be the authoritative foundation dataset that we come to expect. Formats. Cloud and open data standard formats have democratized 3D model exchange and use in applications such as digital twins and smart city applications. However, desktop formats are still required. Firstly, a geodatabase being the authoritative storage of these datasets. Then, open desktop formats like IFC and Wavefront OBJ, Collada DAE, as well as proprietary formats used by engineers and designers and architects, such as Autodesk, Revit, Rhino 3D. CityGML, a word that scares many of us. CityGML refers to both a building data model, its geometric structure, and it is also a format. I've added it here today because it's a way of thinking about our building models independently of the format itself. Basically, a building model doesn't need to be a single object. The CityGML model on the bottom left is an LOD 2.3 model, and it can be broken up into its individual features. Walls, roof, a building part, such as roof furniture, and the ground surface, highlighted in blue. This blue ground surface describes the floor space of the building, independent of its roof structure and its awnings. Building models and their interoperability with other 3D datasets. There will unlikely be a one-size-fits-all building product. Building datasets, however they are to be defined, will not be the end of the story. They will be interoperable with other 3D datasets. Most common example is a development application model. In 3D software and digital twins, planners will be able to delete an existing LOD2 model and place in the new future state development application model. Also, like aerial photography and LiDAR, photomeshes will play a critical role in analyzing and visualizing in 3D. Here is an example of interoperability with a photomesh and building footprints, LOD1 models. A photomesh is a single object that doesn't inherently allow attribution linkage. But when you combine it with vector data such as a building footprint, it can be classified. Here is an example from Aerometrics from their website. And here is another example from Terra Explorer. Here we have a photomesh, a single object. And here are some existing building footprint datasets from a GIS with attribution. And now we're starting to classify the photomesh. And when you using that building footprint, when you click on the photomesh, you're clicking on the underlying GIS vector datasets and its attribution. And here is the end result. It's important to note in this case, the LOD0 footprint model needs to exist first before this classification can occur. Another important dataset we haven't talked about yet is 3D cadasters or 3D strata plans, strata models, created from our 2D strata plans or legal cadastre. We can also create a legal representation of the land title, representing a building model. This dataset also has its challenges. Strata plans are only in 2D, not 3D, and they are tremendously complex to understand, even for surveyors. On a plan, individual apartments might refer to height above ground, without that ground point being clearly defined. The position of an individual unit might refer to the center or edge of the wall casement, not an easting-northing in elevation in 3D space. Although this dataset is not remotely sensed, a remotely sensed as-built representation of the building shell, it does have tremendous applications in the GIS world, or even for the general public. Imagine a real estate agent being able to clearly define to a buyer the location of their potential investment and access to light, or booking an Airbnb and visually viewing the approximate view of the harbour from your window. So the question remains how a building dataset should be sourced. Excluding the last slide, today I've been talking about remote sense datasets, the LOD0, LOD1, 2, and 3 models, created from aerial and satellite imagery, LiDAR data, UAV and drones, or even from a Photomesh. But there are other non-remote sense datasets. The 2D plans and recreated 3D strata models, development application models, and BIMs, or an as-built BIM of a building. All these datasets and their sources work independently. They are interoperable with each other, and they work together to holistically describe the built environment. Remote sense models, DA BIMs, and 3D cadasters all have their own use cases. From a survey and GIS perspective, remote sense models provide the single point of truth defining the built form as it exists. The question we need to answer is, where do we draw the line in the definition of a buildings and settlements product? We then need to decide how governments source these datasets. State governments definitely have a role to play in funding and centralised procurement, especially for something like a consistent statewide LOD0 or LOD1 building footprint dataset. But when it comes to LOD2 models, many of these datasets already exist over our significant commercial precincts. They are created and managed by local governments, but also produced by some state government agencies or for big build projects. Many local governments have been leading the way with providing their 3D city models as open data, but other state government agencies or big build projects are not. There needs to be a sharing ecosystem where state and local governments work together to fund the creation of 3D buildings, avoiding duplication of investment. Also, we need to work towards a universal standards. Standards not only for how we describe models and model types and their detail, but also metadata accuracy and formats. The 3D buildings product will need to be interoperable with development application models, design BIMs, and as-built BIMs. They also need to be accessible for download through a range of data share technologies, and, of course, be available across the cloud, viewable in digital twins. The 3D buildings product will also need to be dynamic, adjusting to new advances in technologies, especially in the machine learning space. It is definitely an exciting time to be working in 3D GIS and digital twins in Australia. In Australia, through our amazing local governments, they have been truly world leaders for over 10 years. They have been leading the way in 3D model creation, 3D GIS workflows, software tools, research and development, and open data standards. But now it's time for state governments to bring all the stakeholders together to create this sharing ecosystem, an ecosystem of 3D models and federation of digital twins. That's it for me today. Hope this video has been helpful. Please see the video description below for relevant links and my contact details should you want to get in contact. Thank you. See you later.